Hello you guys, welcome you guys come to my Thermodynamics assignment 3, the team project. Um, Although I'm doing this alone, the topic today it is about the phase diagram. Let's move on. So, as we all know that every substance has three basic phases. The first state it is solid state. As I have a figure here, represent the solid state that you guys can see that the blue circles here they connect to each other and they touch each other. There's very little distance between those. As a result, we can conclude here that the connection between them are very strong. It's very hard to break them into pieces. As a result, once we want to move a substance in a solid state, it's become very hard. If we want to move it, we need to move them as a whole thing. Next, we have the liquid state. For liquid state, the connection between each element become lighter, and because it's lighter, it's become easier to break them down. It also means that it's easier for each element to move freely in whatever direction that they want. They don't need to always stick at a piece like the solid state to be able to move. Then we come to the gas phase. The gas phase here, each element is the most has the most freedom. They can move in whatever direction they want because the connection between them and the other elements becomes so weak that they still has that this connection is always strong enough to keep the shape of the substance, but it's not really as clear that the normal people eyes can see the shape of it as compared to the solid state or the liquid state. So we now agree that the phases of a substance are determined based on the temperature and pressure. When we think about water, we see that if water we put it on this under the sun's side, and for sure it will get warmer, hotter and hotter, and then if we can feel that if it's just liquid water, we can feel that the water getting warmer, and if we boil the water, that vapor will appear, and then if we take an ice from the fridge and then we just put it under the sun so it will be melted. So those phase changes that we can feel, and we can feel for sure that it's affected for sure by the temperature. How about the pressure? Well, if you want to think about how pressure affects this shape or the state of a liquid or the state of a substance in general, you need to think about the shape that I show you in the three figures. Never mind. So as you guys now are familiar to the table, the property table, this is one of the examples we have that a space is actually based on not only about the temperature and on the pressure. It's also based on the specific volume. It's also based on internal energy. It's also based on the entropy and entropy. However, they are mutually dependent. Not all of them are, I don't know. Okay. Cheers. In order to represent this relation, we have three type of diagrams. The first one, the second one are pretty the same. They are the pressure specific volume diagram and temperature specific volume diagram. The only difference between two of this diagram it is the position of the pressure and the temperature line. For the pressure and specific volume diagram, the vertical axis is the pressure, and the dashed lines that we have here each dashed line stand for a value of the temperature, and each line represent a constant value for the temperature. So don't be confused that you see on this line, for example, stand for T1 that you see, it is at this point a bit higher, at this point a bit lower, but actually the temperature value are on this line are all the same. Okay, so and on the temperature and specific volume diagram, they also work in the same way. That the the vertical axis you have here, it is the temperature, and the dashed line you have here, it is stand for the pressure, and the pressure, as we discussed for the dashed line before, that is stand for a constant value. So which means the pressure at this point and the pressure at this point, as long as they are on the same line, so they are still okay. They are still the same value. Okay, so what this graph can tell us about the state. So when we find that the pressure and the specific volume, it is in this region over here. So, okay, that is not on light, it is bounded by the light actually. So at this area, it is stand for number 1, it is a subcooled liquid region. And when it touches the light at here, it will start the saturated state. On this left at the critical point here, it is called the saturated liquid line, and then on the right is called the saturated vapor line. So any value between these two lines inside this region is called the saturated mixture, and with the X stand for the quality of the mixture. Then what we have, it is the region number 5 here. It stands for the superheated vapor region. And once again, you guys can imagine the region as this one is bounded after the critical point. This one is bounded from the critical point to the part that are on the right here. Okay, so now we move on to question. So now we have critical point, we have the superheated region, we have the saturated region, we have the subcooled region, but there's still one thing that is missed here. It is about the triple point. So why is that triple point here? That's our question. So to answer this question, that we now have the PT diagram, and it is the perfect thing. It's on the horizontal axis we have the temperature, on the vertical axis we have the pressure, and this one is independent from the volume. And so for any of the combination of the temperature and the pressure, which will result in some point in a region or maybe on the line, but as you guys can see here, this part stands for the ice, this part stands for the liquid state, and this part down here stands for the gas state. And this is our triple point. That's at the triple point, what happened that we can reach, that we have the 3 states at the same conditions. This is a bit tricky, but I would suggest you guys to search this on YouTube, because I found there is very useful resource on YouTube that can show you guys about how the triple point and how critical point looks like. I will leave this link in the description of the video. Okay, so because this PT diagram can perfectly separate as well as represent all the state of a substance. So it is the orange diagram which is called the phase diagram. So when we know about the phase diagram, what exactly we can do with it? The first thing, you can determine the temperature based on the pressure, or vice versa. You can have the pressure, you have the state, so you're gonna look for the temperature. For example, if the question gives you that you have a lot of water that you take from the sink, so it will be saturated liquid water, and the pressure maybe at 101 at this point, and now they ask you that what will be the temperature, so you just project it on the horizontal axis and you found that if it is liquid water and the pressure of that water is 101 kPa, it also stands for 1 atm by the way, so the temperature must be 100 degrees Celsius. The second thing we can use, it is from a pair of temperature and pressure. We now can define the state of the substance. Okay, so that's pretty everything that we can use with this diagram and this phase diagram with a little support from the table in order to figure out the value of the pressure and the value of the temperature. Otherwise, it will become a little bit useless. Okay, so let's think about this in this way. When we boil our water or when we cook something, that the first thing we need, but let's take for a specific example here. It is when you cook your soup, so you might want to add some water. It's about the temperature of water in room temperature is normally about 30 degree about this point, and now we want to cook it, so you want to boil the water. So the question here it is, you should cap the bowl, you should cap your pot, or you should leave it open. So in order to show you this, well, based on our graph here, you guys can see that if it is at this point, and now you're raising your temperature, when you raise your temperature, for sure, the pressure will increase also. So our hypothesis here it is when you cap your pot, your temperature will suppose to raise faster. And let's see that whether it is correct or not. I have done an experiment here on thermodynamics. So the key here that I want to prove that when there's a change in the pressure, that will lead to a change in the temperature. With what we're working on today, it is just water, and this is just the tap water that I take from that tap. Okay, so basically the target, we will boil the water 2 times. The first time without the cap and the next time with the cap. And we will use a watch, this one, a digital watch, so that we can check which one will cook the water faster. And well, the case that the water boils faster, it also means that the temperature of the water is higher. Maybe some people will discuss or debate that actually when you cook water on the mountain, it will be like the temperature for the water to be boiled, it will be lower compared to somebody who cook water at a lower altitudes compared to the ground. But we will just do our experiment here in this kitchen, which means altitude has nothing to do here. Okay, so let's get started. Turn it on, put the water in. Okay, and let's start our timer. It cannot take long. I hope you guys can see that there's some boiled water. Actually, there's some gas that. Oh, I don't know the right word to talk about this. It is vapor. That's right. That's the right word. I hope you guys can see that there's some vapor that vaporizing. Yep. So hopefully the water will be fully boiled within 1 more minute. Okay, start boiling. There are more and more vapor. Okay, so I think I can stop at the 5 minute. Thus, wait now for the first carry. Take 5 minutes for the measure of the liquid water turns into vapor. In other words, just we now start seeing a lot of bubble on the surface of the liquid. Now let's try again and let's see what we found. Take some amount of water. Make sure that it meets the line. Yeah. Now I need later more. Okay. Let it become stable. Oh, why? Yeah, now it's good. And now we start our experiment again with closing the cap. And let's see how long it would take. The first recorded 5 minutes. Now we can start again. I didn't close. Oops. Okay. Leave it for another 1 more minute. Okay, 1 more minute to 2.5 minutes. Let's see what we got. Can we see something from here? No. Sorry, you guys. but I can start seeing some bubble on the cap, so hopefully we receive a positive result for this time. If I stop the watch at 2:30 and we have a lot of bubble on the surface, so which means our experiment meet the theory. And 5, 4, 3, 2, 1, stop. Okay, let's check what we got here. Okay. That is, you can see there's a lot of bubble, and that is. Thank you guys for watching. So after this experiment, I hope you guys are all convinced by the phase diagram that when we increase the pressure, then for sure will lead to an increase in temperature as you just move along the line. Thanks for watching.